In the last two mini-lessons, we saw applications of Newton's second law to one object in equilibrium and to one accelerating object. In this mini-lesson, we work through another example, but now involving two objects. Another new feature in this example is the presence of kinetic friction. The example reads, Mr. Wilson is giving his twin sons, Luke and Owen, a ride on their sleds. He is pulling on rope A, attached to Luke's sled, which is attached by rope B to Owen's sled. Each boy and his sled have a total mass of 65 kilograms. Rope A makes an angle of 18 degrees with the ground. Both sleds are accelerating forward at 0.75 meters per second squared. The coefficient of kinetic friction between the sleds and the snow is 0.12. What is the tension in each rope? As always, we start by sketching the scenario presented in the problem. This problem has two objects whose motion we need to analyze. Luke and Owen, or technically, Luke plus his sled and Owen plus his sled. We don't really need to analyze Mr. Wilson's motion, though in principle we could. We just treat him as the source of propulsion for Luke and Owen, the result of which is the 0.75 meter per second squared acceleration of all of them. Now that we have a sketch, we need to identify the forces acting on each object of interest. We'll start with Owen. Gravity exerts a downward force, and the snowy ground exerts an upward normal force. The tension in rope B exerts a pulling force to the right, while kinetic friction between the sled and the snow exerts a force to the left, opposing the motion. Now let's consider Luke. Gravity exerts a downward force on him as well. And the snowy ground also exerts an upward normal force. Notice that I made the normal force vector on Luke shorter than the one on Owen. That's because the normal force on Luke is weaker than the normal force on Owen. We'll see why shortly. The tension in rope A exerts a pulling force to the right and up. Since the rope makes an angle of 18 degrees with the horizontal, so too does the tension force vector. In addition to showing the force vector itself, I've also drawn in the horizontal and vertical components, which we'll need shortly. The tension in rope B exerts a pulling force on Luke to the left, and so does the kinetic friction force between the snow and Luke's sled. Finally, both boys have the same acceleration to the right. A equals 0.75 meters per second squared. These sketches with forces identified are nearly free body diagrams already. It's a very simple matter now to complete the steps in creating free body diagrams for the two objects. And here they are. Notice that I've included coordinate axes for each object and represented each object as a large dot at the origin. Vectors for the forces acting on each object are drawn emanating from it. Furthermore, all force vectors have been resolved into components along the coordinate axes. Actually, the only one that had to be done for was the tension force due to rope A, since each of the other forces already point along a coordinate axis. Kinetic friction acting on a sliding object can always be expressed in terms of the normal force at the same interface. In particular, the kinetic frictional force is equal to the coefficient of kinetic friction times the normal force. So we replace the labels F sub O and F sub L for the kinetic frictional forces acting on the two objects with mu sub k n sub O and mu sub k n sub L respectively. There are a bunch of symbols appearing on these two free body diagrams. Let's classify them into ones that are known and ones that are unknown. The problem gives us values for the mass, acceleration, and coefficient of kinetic friction, and we know the value for g. However, we don't know the values for T sub A and T sub B, the tension in the two ropes, or N sub O and N sub L, the normal force of the ground on each boy in his sled. So there are 4 unknowns in the problem. In order to solve the problem, we need to have 4 equations in these unknowns. These are given by applying Newton's second law to each object. Equation 1 is the x component of Newton's second law as applied to Owen. The x component of the net force on Owen is the tension in rope B, T sub B, minus the frictional force, mu sub k n sub O. And this is set equal to ma, the mass, times the x component of the acceleration. Equation 2 is the y component equation for Owen. The y component of the net force on Owen is the normal force, N sub O, minus the weight, mg. And since there is no acceleration component in the y direction, this is set to 0. Equations 3 and 4 are the x and y components of Newton's second law, now applied to Luke. The x component of the net force on Luke is given by the x component of the tension force from rope A, T sub A cosine 18 degrees, minus the tension force from rope B, T sub B, minus the frictional force, mu sub k times n sub L. This too is set equal to ma. And finally, the y component of the net force on Luke is given by the y component of the tension force from rope A, T sub A sine 18 degrees, plus the normal force, N sub L, minus the weight, mg. Again, there is no motion in the y direction, so this is set equal to 0. Now perhaps you can see why the normal force on Luke is smaller than that on Owen. The ground doesn't need to balance the Luke's full weight. It gets some help from rope A. Okay, now we have 4 equations and 4 unknowns, so we're ready to solve. Equation 2 can easily be solved for the normal force, namely N sub O equals mg. Plugging in numbers gives N sub O equals 637 newtons. Now we can solve equation 1 for the tension in rope B. T sub B equals ma plus mu sub k times N sub O. And we now know the value for N sub O. So plugging in numbers, we calculate T sub B to be equal to 125 newtons. Equations 3 and 4 both depend on the 2 remaining unknowns, T sub A and N sub L. We solve equation 4 for N sub L in terms of T sub A, but we're unable to evaluate because we don't know T sub A. Instead, we turn our attention to equation 3. Substituting in the previously deduced forms for T sub B and N sub L gives an equation in which the only unknown is T sub A. Now we isolate the terms involving T sub A on the left-hand side, moving everything else to the right-hand side and collecting like terms. Finally, we divide both sides by the factor in parentheses to get an expression for T sub A. Plugging in numbers gives T sub A equals 253 newtons. We can now plug this back into the expression for N sub L to find N sub L equals 559 newtons. Here we summarize the results. T sub A equals 253 newtons, T sub B equals 125 newtons, N sub O equals 637 newtons, and N sub L equals 559 newtons. We are now able to answer the question posed in the problem. What is the tension in each rope? Well, the tension in rope A is 253 newtons, and the tension in rope B is 125 newtons.